And thank you for joining us for Spa Parts Plus Spa Troubleshooting Video Guides. In the continuing tradition of serving all of our customers' needs, we have designed this series of videos to help both the novice and the experienced repair person learn and review portable spa repair. There are 5 videos in the series. This first video will be an introduction and an overview of how the typical portable spa operates. Again, thank you for joining us for Spa Parts Plus Spa Troubleshooting Video Guides. And now, here's Tim.
Thanks, Barry. As Barry mentioned, in this video, we're going to take a look at how a spa works. We'll also take a look at some of the tools that are critical to spa repair and how those tools are used to troubleshoot various components within the spa system. Now, there are 4 basic parts that make up a spa. They are the plumbing, the heating system, the pump, and the blower. As we look at this drawing, we can see that the side drain and skimmer are teed together to supply water to the front of the pump. Water is pumped and filtered, then heated and returned to the spa via the return fittings or jets. The action of the spa is usually controlled by pneumatic, air-actuated, or electronic controls. Let's take a look at some of the tools of the trade, and as we do, notice that most of these tools have insulated handles. We'll start first with what I have in my hand, which is the combination wire stripper cutter. You'll also be utilizing the standard hacksaw and the mini hacksaw. There'll be the needle nose pliers, crimpers, open end and box end wrenches, various screwdrivers, again with the insulated handles, and last but not least, the channel locks also with insulated handles. Another one of the tools that you'll be utilizing in spa repair is what's known as the ram bit pipe reamer, which we have mounted on this drill here. The ram bit pipe reamer is going to clean out all of the pipe inside this coupling. We've, of course, cut this pipe off already. We'll get in with the reamer and actually clean this pipe out so that we can fit a new pipe in there and have a clean fitting on there. Now, the ram bit pipe reamer has a cutting tool that you can see right here, and ahead of that cutting tool is what's known as a gauge. These gauges are Schedule 40, Schedule 80, and in the case of the gauge that we have on right now, Schedule 200. Let me go ahead and swing our vise around here so that we can drill. Get that locked down, and we'll show you exactly how the tool works, just like this. All right, we're not going to drill through the entire way just for the sake of this demonstration, but let me loosen our vise up again. And you can see, after I clean out some of the burrs here, that we have cleaned out some of this pipe, and obviously we would clean out a lot more of that going all the way back in so that we could have a clean fitting if we were actually out in the field doing this. But you see the whole point behind this particular tool. Now let's take a look at a couple of other tools. 2 of the tools you'll be using in spa repair happen to be the voltage tester, or sometimes known as the multimeter, and the amp probe. And for a discussion on amps, volts, and watts, please see the handbook that accompanies this video. Throughout these videos, you'll hear the terms line and load. Line is the power going into the switch, and load is the power leaving the switch. This is a voltage tester, or as it's sometimes known, a multimeter. We use the multimeter to test for voltage along any given point in the system. For example, if we wanted to test for 120 volts on this Mach system that we have here, we would set the meter first of all to display volts, and then we take our probes, and we have to put one probe on a neutral line down here, and another probe on a hot line, in this case right up here. That'll give us a reading of 120 volts. If we're looking for 240 volts, the probes must go on each of the hot lines, one here, and again, in this case, one here. That'll give us a reading, a true reading of 240 volts. Remember, 120 and 120 do not always make up 240. In fact, let me show you with this breaker box right here. You have to be on opposite poles to get a true 240 volt reading. As I'll show you here in the breaker box, you can see that we have two power lugs on either side of the box. These power lugs have the metallic strips that come down each side. This is where the utility power comes in, is on these lugs right here. If I try and install this circuit breaker improperly, so that it's not actually touching two opposite poles, we're not going to get 240 volts. However, if I bring it up here and install it properly, then we get 240 volts. Now, why is that important? Well, let me explain. For example, let's go back to this case here. If we have a pump and a blower, for example, that operate on 110 volts, that's fine. But you may have a 6 kilowatt heater that needs 240 volts, and it's not going to get it if that circuit breaker is installed improperly. This is an amp meter. The amp meter is a quick way to check if a piece of equipment is operating and if it's operating within the correct parameters. For example, if we have a 120 volt, 1.5 kilowatt element in this particular system, it should be drawing approximately 12 amps. If when we check with the amp probe it's not drawing any amperage at all, then obviously it's not working. Also, again, if we use this display here as an example, we have a 1 horsepower pump over here. It should be drawing approximately 10 amps. If when checked we find that it's, say, drawing 15 amps, well, that could cause wire damage, and it could also cause continually blown switches. Remember, a good technician is going to find out why the switch is continually blowing, not just continually replace the switch. Let's say, for example, a customer has a low-speed relay that is always blowing. Well, one of the things you want to check for is perhaps a pump that's pulling too many amps, say 15 amps instead of 10. That's the cause of the problem, and it must be replaced. Well, now that we're familiar with some of the terminology and some of the tools involved in spa repair, let's take a look at some of the devices in a spa. Let's start with the air button. The air button is simply a switch that creates a pulse of air that activates various switches in the system. Now, if the air button is not activating the switches, then what you need to do is, first of all, test to see if you have a good air button or not. And in order to do that, you very simply put your finger over top of the air outlet for the button, and then you press the button itself, seeing if you have any resistance. If you do get resistance, then the button is okay, and therefore the problem must be elsewhere. It may be that the button is not producing a large enough volume of air to activate the switch. It may be that it's too far away from the switch that you're trying to activate, or it's possible that you could have a hole in the hose that leads to the switch. However, if when you conduct this test on the button you get no resistance whatsoever, that means that you have a bad button and it needs to be replaced. There are two ways to test a heating element, and in both situations we'll be using our multimeter. First of all, let's check this heating element that we have here for demonstration purposes, and we want to check for resistance. So we'll set our multimeter to ohms, and we're looking for between 8 and 11 ohms. We check by connecting both probes to the terminals for the heating element, and in this case I see that we have a reading of 9.5 ohms, so we're okay there. But we also want to check for continuity. So switching the multimeter again, we'll check the meter itself to see that it's working, and in this case we know it is. So to check for continuity or lack of same, we'll attach one of the probes to a terminal and the other to the ground for the heating element. Now you can hear that we're not getting any kind of a signal here, so that indicates that we have no continuity here. That's a good sign. It means the heating element is good. Had we had continuity, we would need to replace the heating element. Now there's another way to test a heating element, and let's come over to this pack right over here in order to conduct that particular test. In this case, I've switched the multimeter to volts, and we're going to be reading for voltage here. We're looking for 240 volts, and in order to get that reading, we will connect our probes to the two terminals that lead to our heating element in this pack, and we can see that yes, we do have 240 volts here. So the next thing we want to do is to use the amp probe. We'll put that around one of the wires leading to the terminal for the heating elements, and if we have 24 amps on our readout here, then we know the heating element is good, And yes, we do have 24 amps. So the heating element in this case is okay. This is a ground fault circuit interrupter, otherwise known as a GFCI. The GFCI is a highly sensitive switch that detects a ground fault difference in the system. GFCIs work by sensing the imbalance between current passing through the hot and neutral lines. An imbalance indicates to the GFCI that some current is escaping from the system. This could create a potentially dangerous situation, so the GFCI cuts the power off. If the GFCI is tripping, disconnect the load hot and neutral and reset and test. If the GFCI does not trip, the cause is elsewhere in the equipment, or it may be a wiring problem. If the GFCI does trip, replace it. If the GFCI trips after running for a period of time, the problem is typically a weak GFCI, and it should be replaced, although this may also be caused by what's known as a warm-up shorting condition in a motor. This is a relay. A relay is a device that, when energized, allows current to flow through the system. There are two different types of relays. There's the circuit board mounted relay and the frame mounted relay, as in this case. Testing for each is the same. Now, if we want to test voltage for the relay, we have to test it at the coil, and we have to test it for the voltage it was designed to operate at. We'll test on either side by using the probes from our voltage meter here. And this is a good time to let you know that circuit board mounted relays commonly operate at 6, 12, 15, and 24 volts DC. While with frame mounted relays, as in the case again here, they operate at 120 and 240 volts AC. Is there voltage at the coil? If yes, and the contacts do not close, replace the relay. If no, test for problems elsewhere in the system. Now let's assume the relay does pull in. If the coil is pulling in, but the component that the relay controls is not operating, test for voltage going into the relay contacts and exiting the relay. Is there voltage on the line side of the relay contacts? If yes, test the load side of the relay. Is there voltage? Again, if yes, the problem is with the component that is controlled by the relay or in the connection between them. If no, simply replace the relay. Coils are the electromagnetic component of the relay, the contactor, or the solenoid. When electrical current passes through a wire which is coiled, an electromagnetic field is generated. In the center of the coil there is a metallic core. This core can move in and out of the coil. When the coil is energized, the core retracts into the coil due to the magnetic force and actuates an arm which makes point contact on the relay. Testing a coil is simple. We use the multimeter to test for resistance between the coil connections, here and here on either side. If there is resistance, then the coil is good. If there is no resistance, then the coil wire is discontinuous and the component is no good. The time clock allows us to set a predetermined time for filtration and heating. However, if the time clock face is not rotating automatically, what we want to do is check for the correct voltage at the time clock motor connections. You'll see those right here. Also, observe the time clock gear if it's visible. And if the gear is turning and the time clock does not rotate, you want to replace the time clock. Manually turn the time clock to check for smooth operation. You want to replace it if that rotation is not smooth. If the time clock rotates but does not turn the pump on, check for continuity using your multimeter between the time clock points when the time clock is closed. If there is continuity and the clock rotates, check elsewhere in the system for a problem. If there is no continuity, replace the time clock. A transformer is a device that takes current in on one end and reduces the amount of current going out the other. To check that, we're going to use our multimeter and check for resistance. We'll check resistance first on the primary side to see if we have any resistance whatsoever. And in this case, we are reading resistance, so we next move on to the secondary side of our transformer. And again, test it the same way, checking for resistance. And again, we find that we have resistance here. So finding resistance on the primary end means that the primary winding is all right. Finding resistance on the secondary means that the transformer is functioning on that end as well. We should look for a problem elsewhere in the system. For example, the air switch, a light bulb, or perhaps the harness. If there was no resistance whatsoever on either side, we'd want to replace this transformer. The thermostat is a switch that allows us to adjust the temperature of the spa water. If the spa does not heat enough, make sure the spa is covered and the equipment door is shut. It's common for uncovered spas not to heat enough due to excessive heat loss. Or replace the thermostat. If the spa does not heat, test the thermostat to see if the thermostat is making. If the thermostat is not making, replace the thermostat. If the thermostat is making, check elsewhere in the system for other faulty components. And finally, if the spa overheats and trips the high limit, check the thermostat for shorted contacts. Micro switches are used in many components in a spa pack. They're used in air switches, pressure switches, and in relays. We'll be testing this micro switch for continuity using our multimeter. We'll test it by placing our multimeter probes into the common lead and also into the normally open and normally closed leads over here. Now, if we have an audible signal from our multimeter, we'll know that we have continuity. First, by placing one of our probes into that lead, the common lead, and placing the other probe into the normally open lead, we'll find out if the switch has continuity when we activate it. And again, we'll be listening for that audible tone. There it is. That tells us that the normally open position is working on this switch. Let's now test the normally closed position, and again, we'll be listening for that audible tone. Now, if I deactivate the switch and lose the tone, that means we have no continuity, and this switch is good. Moving on to air switches now, it's important to know that there are two types. There's the solenoid-driven and the bellows-driven. The solenoid-driven uses a momentary switch, which takes an air pulse to activate the coil that in turn activates the micro switch. The bellows-driven, on the other hand, takes the air pulse and directly activates the micro switch. You can see that here. To test a solenoid-style air switch with a known good air button, then what we want to do is activate the air sensor. If the solenoid does not operate or you hear air escaping, then the air sensor is bad. Also check the micro switch for activation with a multimeter. We'll be checking for continuity, and if we get our audible signal from the multimeter when we activate the switch, we know that we have continuity. If the micro switch makes and breaks as you depress that button, then what you would need to do is check the solenoid-driven air switch. To check the solenoid switch, test the coil using the method that we just learned. For testing coils, that is. Now, if the coil tests okay, then test the micro switches again using that same method that we learned earlier in the coil section. If the micro switches test bad, you want to replace that switch. Don't attempt to service that. If the coil tests bad, replace the solenoid-driven switch. Now, for a bellows-driven air switch, again, with a known good air button, activate that switch. If you hear air escaping from the switch or the switch itself does not activate, replace the switch. If the switch activates and the micro switch does not make or break, you want to check for the proper switch button combination. Make sure that you've got the right air switch for the job. The pressure or the flow switch tells the heater when water is running through the system and that it's okay to turn on. If you want to test the pressure switch, you'll use the method that we learned in the section on air switches. This is very similar to an air switch, it's just that it takes a greater amount of pressure to activate the pressure switch. In order to test the flow switch, we're going to be using our multimeter to test for continuity. The flow switch uses the flow of water to move the gate, which in turn activates the micro switch encased within. We'll use our multimeter now to check, as I said, for continuity when we open and close that gate. All right, and all I have to do now is open the switch, and we see that we have continuity. When I close the switch, there is no continuity. If the switch had been defective, then we probably would have had to replace the switch, definitely would have had to replace the switch. However, it's possible that the gate would not be activating the switch simply because there's not enough water flow to move the gate sufficiently to activate that switch. If that's the case, then we want to look for whatever the problem is that's preventing the water flow to be strong enough to move the gate. By the way, also, these switches oftentimes are adjustable. In this case, however, this switch is not. I'd like to leave you with one last thought. Remember, whenever you're working on a spa, hazards are always compounded by the fact that you are working with both water and electricity. Before ever doing any maintenance or repair work on a spa, make sure that you're thoroughly familiar with the manufacturer's owner's manual. It's important to follow specific instructions and hints on the equipment you're working on. And remember, please, be safe.